Continuing in lesson 8.1, moving on to day 2, we are going to now review what it means to verify a trig identity. Verifying trig identity involves transforming one side of the equation so that it matches the other. And in able to do that, we are going to use fundamental identities, factoring, algebraic manipulations in order to arrive to whatever conclusion um, we have chosen. So for instance, in part A, example 1, we have a trig identity, sine theta, cotangent theta, secant theta, that are multiplying to arrive to the number 1. So when you guys have a equation set up for you already, establishing a true statement, I'm going to want you to verify by choosing one or the other side to basically ignore. You will provide some sort of strike through. In other words, you're going to cross out the side I want to ignore and work on the side that does not have a strike through. And usually what I suggest to students is always choose to strike through the one that is the most simplified side. So between the left and the right hand side of the equal sign, notably, this side is a lot simpler. So I'm going to create a strike through to ignore it, and I am going to work with only these terms. And I'm going to do exactly what I did in day 1 with the hopes that my single term ends up simplifying to this hidden answer key, so to speak. Sine theta, we know that we usually do not even change. So I'm going to just bring this down, sine theta. Cotangent theta breaks down to cosine theta over sine theta. So if anything, have your formula sheet handy so that you can look at where I'm getting these from. Secant theta is the reciprocal of cosine. So reciprocal of cosine theta. And now let's see if when we simplify this, we have arrived to the answer or if there's anything else we need to do. Well, sine theta and cosine theta are both canceling over multiplication. So our answer ends up being a 1 left over, which is definitely what we wanted to end up at. So we're done. There are going to be times, like in part B, where you will have a left and right hand side of the equal sign where it's hard to decide which one to cross through because they both are pretty much the same thing, the same operation, number of terms. So in a situation like this, it does not matter. Just cross out one side. So since we crossed out the right side up here, let's practice by crossing out the left-hand side of the equation. So this is my answer key. This is what I want my simplification process to arrive to. But we're going to pretend that that doesn't even exist, right? That doesn't exist. We just have this problem that we're simplifying to get to this. Now, what I want you guys to realize is in this problem, we have 2 times cosine squared theta minus 1 that has to somehow end up with a problem like this where cosine squared has completely disappeared. It turned into sine squared, right? So you have to use your tools to kind of manipulate to help you arrive to that situation. So let's look at our formula sheet that we had from day 1. And we notice that cosine squared theta right over here can be rewritten so that it is written in terms of sine. So if I moved sine squared over to this side, 1 minus 1 minus sine squared theta would be cosine squared theta, and it would get rid of it, right? So let's do that. Let's manipulate that Pythagorean identity. And I'm going to replace this piece right here. Okay, so I'm going to bring the 2 over. Substitute, I'm going to replace cosine squared theta with 1 minus sine squared theta. I'm going to rewrite that sine squared plus cosine squared equals 1 theta. I'm going to rewrite it like this. So I know 1 minus sine squared theta is the same thing as cosine squared, and then I'm going to bring down the minus 1. And now Multiplication, because of these parentheses, 2 times 1 is a 2. Distribute, 2 times negative sine squared is negative 2 sine squared theta. Bring down my minus 1. And oh my goodness, I'm really getting closer to this answer, right? I'm going to combine those like terms, the 2 and the negative 1 constant. They combine to a positive 1. And I have most definitely arrived to the answer that I had struck through. So I'm going to put a check mark there saying I have arrived and I'm done. This is also verified. Okay, so here's an example where you use substitution and algebraic manipulation to rewrite an equation. Whatever else do we use to help us? So in this set here, you are going to see that we are going to use times and time again, factoring, specifically greatest common factor, which is the case for this problem. So I'm going to strike through this one right here, and I'm going to notice that in both these terms, this term and this term, there is a commonality we call GCF. The cosecant squared theta appears in this term and appears in this term. So we're going to factor it out using the GCF approach. Excuse me, and the GCF approach says, what if I were to divide these terms by that greatest common factor? So I'm writing this really lightly just to kind of give you a visual, but that's what GCF is. You're dividing out. So I'm going to factor out this difference, right? And I'm going to write cosecant squared theta. What am I doing? Cosecant squared theta. So that's my GCF. You always write down what the GCF is. And then in the parentheses, write down the resulting factor, having had you divided out those. So these two divide to a 1. And these terms right here divide, ends up canceling, right? And so cosine squared comes down. And you can always check by backwards working to see if I arrived to where I was. Cosecant squared times 1 indeed is cosecant squared. Cosecant squared times cosine squared is cosine squared cosecant squared. So this rewritten right, this is working out for us, okay? So now, by now, you should recognize that that's a difference of squares. 1 minus cosine squared, going right back again. 1 minus cosine squared is sine squared. That's manipulating that. So I'm going to substitute, just like I did in this previous problem over here. Cosine is 1 minus sine. Gets pretty redundant. If you keep practicing, you will start seeing these really, really quickly. Okay. What about cosecant? Cosecant is the reciprocal of sine. So cosecant squared is the reciprocal of sine squared. So reciprocal of sine squared times sine squared. These are going to cancel, results in a 1, which is what I struck through above. Okay. All right. And let's move on to where we sometimes just need to straight out simplify in order to condense into a single term. In this simplification process, we are going to distribute. The first times the first term, the outer terms are going to multiply, the inner terms, and then the last terms. So distribute, which a lot of you guys like to say when you multiply binomial times binomial, you like to call it the FOIL method. First, outer, inner, last. So let's distribute. 1 times 1. Oh, I forgot to put my strike through. Always strike through which one you're ignoring. 1 times 1 is a 1. 1 times cosine is a positive cosine theta. Negative cosine times 1 is a negative cosine theta. And negative times positive is a negative cosine squared theta. Cosine minus cosine zeroes out, so it's going to disappear, right? And now we have 1 minus cosine squared left. But y'all know that that's a Pythagorean identity. of sine squared theta. And that is definitely the reciprocal of cosecant squared theta. And so once you have written the answer to your problem by striking it out, you know to stop. If you recognize that this was difference of squares and you just went straight from here to here, that is completely first worthy to be applauded, but totally okay in doing so. If you notice this was an A minus B, A plus B format, and you recognize that that merely was you doing this problem for sine squared. So remember here, where are we? Right here, 1 minus cosine squared is 1 minus 1 plus cosine. Well, isn't that what that is? 1 minus 1 plus. So if I can kind of double this paper here, maybe I can show you better. So there we go. See? So there is 1 minus 1 plus 1 minus 1 plus. What is that? Sine squared. So replace this whole thing by sine squared. So you would have skipped all this, you would have ended up right here being telling me it's a reciprocal. So anytime you guys have two subtraction a difference of square problems, you know it's going to be one of those trig functions. So it could be sine squared, cosine squared, tan squared, or cotangent squared. Can all be rewritten as a difference of squares. All right? So look out for those. Last but not least, take a moment, please, and I would like you, please, to take a trip back to elementary school, and I need you to add those two fractions for me. So pause the video now and come on back. Okay, check your answers. So the big walk away that I want you to gather from doing this problem is basically recall that when you are adding and subtracting fractions, you must establish a common denominator between the two in order to combine them. So right now the denominator were distinct, one being a 3 and one being a 4. So what you had to do was to choose the lowest common multiple between them, and that was a 12. So what do I need to do to get 3 to turn into a 12? Well, I'm going to multiply that denominator by 4, but I must do it to the numerator as well if I want to have a consistent ratio of a multiplier of 1. I don't want to change this problem, so 2/3 times 1 will still remain 2/3. So I must multiply by 4 on top and bottom. Likewise, 4 needs to turn into a 12, so I need to multiply it by 3. So I must establish that it's a multiplier of 3 divided by 3. So 3/4 times 1 still remains at 3/4. So me inserting these numbers does not change the original problem. The denominators now are a multiple of 12, so you can combine them so that you get a numerator of 8 plus 9 turning into 17. So this addition of these two terms, those two numbers are equivalent to 17/12. So that's basically what I need you to gather from doing this next problem. Notice that cosine and sine are both distinct denominators. They are not the same denominator, so we cannot combine them in order to bring them together into a single term. So I'm going to take 1 over cosine, and I'm going to multiply it by the denominator sine theta. So I must do it upstairs as well, based on the reasoning I gave you earlier, plus 1 over sine theta. I'm going to multiply top and bottom by cosine theta. So that's a 1, that's a 1, didn't change the problem, right? That's a 1, that's a 1, so it's still the original problem. And now, notice that my denominator is a cosine sine, sine cosine, order does not matter, okay? Multiplication is commutative. 2 times 3 is the same thing as 3 times 2. So 1 times sine is a sine theta, plus 1 times cosine is a cosine theta, over their common denominator. And whether you write cosine or sine first does not matter. So this right here is the simplified answer. And you can't go any further than that. Second to last one. Let's move on over here. So let's put a placeholder here under tan theta. So again, not the same, right? So I am going to take this tangent theta over 1, multiply by tangent. Why? Because I want my denominator here, the number 1, to match this one. So I'm going to multiply it by tangent and need to do it upstairs as well. And it so happens that this other fraction can just sit tight until we get the other one with the common denominator so that we can bring them together. Okay, so this is going to turn into tan squared over tangent, right? Tan squared over tangent theta. So I'm going to write the tangent theta because they both have tangent theta, right? And put my minus, and I'm going to put tangent squared theta minus secant squared. So if you're like, oh, Pythagorean, let's go over there. You're absolutely right. So we're trying to get what? Tangent squared minus secant squared, right? Tangent minus secant. So tangent squared minus secant squared, we're going to definitely use here. There's no tangent here, no tangent here. So tangent squared minus secant squared. So that means if tangent squared has to be subtracting secant squared is coming to this side of the equal sign. And that means this plus 1 has to come over to this side. So notice how tangent turns negative, which is what we needed, right? I'm going to come over here. Tangent squared and secant, I said tangent turns negative. Tangent squared combines with a negative secant squared, because secant squared is going to come over, and that's going to look like this. And it's going to equal what? Well, this plus 1 has to come over, and what's it going to become? It's going to become a negative 1. So I need to put tangent squared minus secant squared is actually negative 1 over tangent theta. And then 1 over tangent right over here, you can't see, right there, is cotangent. So negative 1 over tan would be negative cotangent theta. So let's put negative cotangent theta. And we will circle that answer. And it is my hope that based on what you did in 8.1, when you looked at D, you celebrated because these are reciprocals of one another. So there should be, I wish I was a really good artist and I can just do like celebratory fireworks or something like here. But that should bring a smile to your face because we are multiplying reciprocals. And we love the shortcut, not multiplying, my bad. We are dividing reciprocals. So that should bring us much joy because we know that when we divide reciprocals, we always find out what the numerator is and square it. So tangent over cotangent, that's just going to be tangent squared theta plus 1. And then, oh, voila, there's that 1, there's that squared term. Hopefully now you're seeing, oh yeah, anytime I have a square term and a 1 and they're adding or subtracting, I know to go to the Pythagorean identities. And lo and behold, there we are. Right there, tan squared theta plus 1 is what? It's secant squared theta. So tangent squared theta plus 1 is secant squared theta. And right there is the end of day 2 of trig identities. You have gotten more of an extension of verifying and practiced a little bit more with simplification. Thanks for watching, and again, turn to your homework on the last page of this package.